Okay, good. I'm Massimo Torquati from University of Pisa, senior partner in Admire, the Admire project. Today I'm going to show you to describe a little bit the CAPIO middleware entirely developed within the Admire project. CAPIO stands for Cross Application Programmable I/O. Is meant basically to coordinate I/O in workflows application. Outline of the talk is one. First, I will give a little bit of context, defining workflows, traditional versus in situ workflows. Then I introduce CAPIO, its feature, its runtime, and a little bit of experiment that we did in the last period. So to start, a little bit of context, as I said. So what is a workflow? A scientific workflow in a nutshell. Basically, is a DAG, directed acyclic graph of application of software components, usually called jobs, tasks, steps, etc. In the picture here, you can see obviously an example, another example, where I sketched some components, 5 components, so 5 steps. Let's say S and Y are parallel, internally parallel, maybe they are parallelized with MPI plus OpenMP. Then we could have some like W, a sequential component that can be replicated many times, or we can have strict sequential components like Q in the pictures. The arcs, the edges in the pictures are data dependencies. So for example, W, before starting the W modules, we have to have the data coming from S and Q. The age also describe data models and data transport. So these data need to be moved and they have a shape, a format. And so we talk about data models and data transport. Data transport could be files or could be direct messaging between modules. We say that is a traditional scientific workflow where basically we use as a transport layer the file system. So basically the distributed or parallel file system is used as a communication media. And the workflow management system is the tool that enforces data dependencies, deployment, and scheduling of the modules. It leverage basically files and directories for exchanging data. The advantages of this model, traditional, let's say old style, if you want, is that basically it's very portable because we can for sure develop our application but standalone, and the same application can be used inside a workflow without touching nothing, basically, okay? Because we leverage on files. On the other hand, lots of optimization that you can imagine are not possible in this case, because, for example, if we want to exploit some form of pipeline parallelism between these different components with the file system, it's quite hard. And an additional point is that here the synchronization between modules is strict. We call it on termination, in a sense that we have to, for example, for the Q step in the picture, we have to wait that gets in input the data from S. We have to wait that S stops, finish, basically its execution. Okay, so the coordination semantics is quite strict. The modern way of developing workflow is called in situ. Basically, the file system, the distributed file system is bypassed in favor of using faster in memory or network communications. Okay, for example, using direct messaging or data staging or whatever. Okay, the advantage is that lots of optimization can be applied. For example, overlapping I/O with computation. We could use tailored data format and more efficient data format when exchanging data. We can move only the needed data and not all the data that are in the file system. We can exploit also parallelism in terms of pipeline parallelism. We call it data streaming. The drawback is that you basically need to modify or adapt at least the steps, the code of the different modules of the applications. And this can be time consuming. So for sure, the new approach, the modern way of developing workflow is for sure the best option if you want to maximize performance. There are many tools that have been developed, HEDIOS, Conduit, ParaView, Catalyx, DataSpace. There are many work on these directions. But the point is that it is not always possible to modify the code, or is not desirable. For example, because the application module is legacy, I don't have the source code, or maybe the changing that I'm doing in the source code will not be accepted by the maintainer. So I have to repeat the modification for every new version of the code. And so what can we do in traditional file-based workflow to introduce optimization that are present in situ workflow without touching the code? And in this context was born CAPIO. So basically, CAPIO is a data transport middleware enabling I/O coordination, and so allows to introduce some of the optimizations of the in situ workflow without touching the code. There are pros and cons for doing this, obviously, as always, but we try to do this kind of things by leveraging an external coordination language. So we don't modify the code of the application, but we try to coordinate the I/O through a new coordination language that use a JSON syntax, basically. And now I'm trying to give you the idea on how we can do this. Oops. So basically, again, the idea is, let us concentrate on the part of the workflow S and Q. This is let's say the behavior in the classical traditional workflow without CAPIO. So basically, we start S, the module S, that produce the red bars that you see in the picture, produce files. Those files will be read by the Q module later. When after the S module stops, finish, okay? What we can do with CAPIO instead is to co-schedule both S and Q together, so execute them at the same time, but the CAPIO runtimes makes Q to wait for the file that it asks. Okay, so basically the first file that is produced by the S module will be read by the Q module at the right time. Okay, so we have a kind of synchronization, of implicit synchronization, and this kind of synchronization is introduced, as I was saying, by using a coordination language. Okay, that is what we call CAPIO configuration file. This coordination language, or data model, if you want, or coordination model, describes in a JSON format both data dependencies of the modules, of the steps that we want to take into account when using CAPIO, and the data synchronization, what we call here commit and file annotations and filing annotation. So with these strange symbols in the picture here are the annotations that we provide through the coordination language for introducing the synchronization that we want. So basically we have temporal, the symbol, the annotation defines temporal behaviors. We have defined, I don't want to bother you too much on this, but we define a set of commit annotation and filing annotation. First, commit, what does it mean? Commit annotations or commit rules define when there are no more updates in a file. So basically, in the jargon of the data streaming, we have defines basically the commit annotation, the end of stream. So when a file can be seen as a stream of data, so when the file is completed, we say it's committed, completely committed to this. And we define different commit policy. Obviously, it's on termination. So when the step of the workflow terminates, obviously all the files have been produced. But we can define also commit on close. So we state that the file can be read as soon as it is closed. Okay, so we relax a little bit the semantics, the synchronization semantics. What are filing annotations? They define when a consumer can start accessing the data. Obviously, if the step, the application terminates, so the commit rule holds, obviously the filing rule holds. But we imagine that you have some files that are just, the data is appended on the file. So you never override the file. So you can start reading the data immediately, as soon as the data is produced. And we call this behavior filing no update. So here we relax even more the synchronization between producer and consumer. Who has to define this synchronization semantics is the user, but not touching its code, but writing a separate file. That's the point. This is the syntax of our language with all this annotation for the example sketched here in the picture. That is a toy example. There are many details, too much time, and probably too not so interesting, let's say. Let's concentrate just on a piece of our workflow. So we have a step called up B and a step called up C. Up B produce two things. A file called file C, let me get the pointer, a file C, and a directory containing files, 100 files, okay? So we define in the syntax output streams. So what the module B produce, one file and a directory containing files. Then for each of them, in theory, we can define a filing rule and a commit rule for each file. But in this case, we have a special rule for the file C that we say for the file C, the commit is on termination and the filing is on close. That what does it mean? It means that this file C can be read only if the application B terminates. So here the synchronization is very strict. On the other hand, on all the file contained in the directory dir, the upper bound of the file contained in the directory dir is 100. If it is known, you can provide this hint. Otherwise, if you don't know how many files will be produced, you don't give this hint to the runtime. For all of them, the synchronization is much more relaxed because the file can be accessed, the content of the file can be accessed immediately as soon as the data is produced, because the commit rule is on close and the filing rule is no update. So basically this file will be written one time by one producer and never overwritten or modified. Okay, the user say this. This is true for all the 100 files, but one file in that directory, the file D contained in the directory dir, has a different behavior. For that specific file, we know that we need to be more strict. And so the user can say, okay, the commit rule is on close, so you can access the data as soon as the data is, the file is closed, but not before, because the data on the file will be updated many times. So you have to wait, basically. So here we relax a little bit, and obviously you can go on in this way. So the granularity of the synchronization can be either the entire directory with all the files in the directory, or just some file that you are interested in. Then, okay, I hope you understand a little bit how the idea, how we realized this thing. But from the runtime standpoint, basically, we use the same techniques used in the previous Gecko file system and Hercules file system, the same techniques. So we intercept the system codes of the applications, okay? So basically we define we call this CAPIO dir is a kind of mount point where all the files contained in that directory, all the system call to files contained in that directory will be intercepted transparently, and through the coordination file, the semantics is enforced by the runtime system. Okay, so for the application, it's totally transparent. Just an idea of the deployment. So basically here we have a simple example of two-node cluster where we deployed part of the processes on one node and part of the processes of our workflow in another node. Then we have our CAPIO dir for intercepting the system calls. Then the system calls are the data intercepted by the system call through POSIX shared memory will be passed to the local CAPIO server that knows the information contained in the CAPIO coordination model, the configuration file, and enforce the semantics. So if the process has to wait, he will make it to wait. If the data is available, CAPIO server will provide the data to the process. In case, communicating with other CAPIO server that are in the other nodes through MPI. We have one single backend at the moment, and this backend, the communication backend, is based on MPI, in particular to Open MPI. Good. Now let's see if all these kind of things give a payoff or not. So we did some tests on two clusters. One, what is called Torino cluster, indeed is the HPC4AI cluster present in Torino. Is a tier 3 supercomputer with a BGFS parallel file system. And the first one instead is a tier 1 supercomputer, the Cineca Galileo 100. Both the first one, the Galileo 100, has an InfiniBand network. Instead, the HPC4AI cluster has an Omnipath network, both 100 gigabit per second. Different configuration. The first one is a kind of prototype of supercomputers in a sense that it is very much used by thousands of users. So the network is really stressed. The file system is really stressed, as Mark was saying. So the file system is slow generally because all the application running on this big cluster use intensively the file system. In the second case, in the HPC4AI cluster, basically it's kind of in-house cluster. nobody or few people, let's say, use the classes. So we have almost all the bandwidth available, and the file system is configured in an aggressive way. So you have lots of bandwidth. So this is interesting. So we can compare, let's say, the performance in both situations. We made some tests. The first kind of tests that we made are simple benchmarks, okay? And we benchmarked the communication, classical I/O pattern or communication pattern. So as sketched in the picture, one-to-one, that is point-to-point or producer-consumer, call it as you want. The second one is a kind of gather. We call it many-to-one, so we have many writers, one reader. And the third one is a kind of scatter pattern, so you have one writer and many readers. We use the configuration file sketched here on the right-hand side of the slide. So it's very simple. We consider one directory and all the files in that directory using the commit on close, and then we vary the mode. So the firing rule here can be update or no update, okay? And we enforce two different semantics. The results we obtained, here I reported just some of the tests that we made. And for example, here we can see the one-to-one test using 100 files, each one of 100 megabytes. In the middle, we have 10 files of 1 gigabyte each. And in the last one, we have one big single file, let's say of 100 or 10 gigabytes, sorry, not 100. So the red bar, the first bar is the file system, Lastra in this case. The second bar is CAPIO with the firing on commit. And so in the third bar is firing no updates. As you can see, and then we have the one-to-many and many-to-one here. Okay, so as you can see, basically we consistently behave a little better, I would say, way better in some cases, of the file system, with respect to the file system. So in this case, the code we execute with the file system is exactly the same of the code we execute with CAPIO. With the difference is just this file here, okay? Here, one thing to notice, maybe I didn't stress this too much, and that the files are written with a chunk granularity of 1 megabyte. We did some tests also with some smaller granularity, for example, writing file at 1 kilobyte at a time. Obviously, the file system in some case behaves even worse with such a small granularity of writing and reading. And this is the first test that we made. The second test is instead of the HPC for AI cluster. I'm going to describe what we did, but here we had also another test. We want to see how much we are far from using an in situ tool that is ADIOS tool. So we repeat our benchmarks, one-to-one, many-to-one, and one-to-many, using BGFS, using 100 files of 1 gigabyte, so in total 100 gigabytes, with a write throughput of 1 file, so 1 gigabyte per second. And the granularity, the writing and reading granularity is 1 megabyte always. And we compare with CAPIO with the best, the most relaxed synchronization semantics, that is the firing not update. For ADIOS 2, we use the latest version, 2.9, using BP5 engine. That is basically produce a kind of special data optimized data format, and enable streaming between producer and consumer, okay? And the backend of the ADIOS here is the file system itself. So ADIOS enables streaming using the file system. So what we obtain are these results here. So basically, this is the first table. On the top is one-to-one, then one-to-many, and then the bottom many-to-one. The first one is on 2 nodes, obviously. The second and third one results are on 21 nodes. So 1 for the producer in case of one-to-many, and 20 for the consumer, and vice versa. So as you can see, we are consistently better than the file system. So FS is BGFS, and as expected, I would say, and also as expected, we are worse than ADIOS 2. In all cases, but one-to-many. In that case, ADIOS is lower. We don't know why, to be honest. We don't know why for that case is lower. Maybe it's a kind of pattern not optimized in ADIOS. But the one point is that while we execute for the file system and CAPIO exactly the same code, for ADIOS, obviously we had to modify the code. And here is a code snippet of what you have to do for reading and writing files. So there is a syntax very well engineered, everything fine, but you need to modify the file for obtaining the extra performance that you want. But anyway, we are not so far, let me say, at least in the configuration that we tested, with the small number of nodes that we tested, we are not so far from ADIOS without changing the code. Last thing that I want to show you, and this is related to the Admire project, the weather forecast visualization workflow. In this case, we have an application that is a Fortran-based application that uses MPI for communication. This is called WRF, WRF, that stands for Weather Research Forecast. It's a tool used in almost all the weather forecast simulations. This code cannot be touched because the developer don't trust your modification, basically. That's it. So you can modify the code. The code is open source, obviously, but then the modification will not be accepted by the developer. So usually in the visualization workflow that we have in the HEMP application within Admire, one of the use cases of Admire, we use this visualization workflow in this way. First, we start WRF that produce all the files. Then we start a Python script that goes over all the files produced by WRF and produce a PNG images in this way. And so you have the results that you can see in the website of the weather forecast you prefer, okay? What we did is that, why not using CAPIO for doing this? So we coupled them, WRF and the visualization part, the post-processing, let's say, are coupled together, using also all the files produced by the WRF will be inserted in the CAPIO dir, and then as soon as the data is produced by the WRF application, we can execute the visualization, the Python script, the visualization tool, sorry, not the visualization tool, the tool that produces the PNG images. This is the configuration file used. Basically, the point is that since WRF writes the file many times, so the file is updated, we have to use the semantic on close, but update. So firing on commit. So it's not the most relaxed semantics, because in this case it doesn't work, because WRF, a single file, will be rewritten and updated many times. But what you obtain is something like this. So you first obtain the first images quite immediately, then some other images, and then other images. And so it works using streaming, okay? So basically, the time that we obtained for a kind of on 4 nodes with the 96 Fortran MPI processes are this way, are these. So basically we save about 50% of the time. But the good thing is that while in the standard version, let's say not the standard, but in the old version, let me call it, the first file is available after 700 seconds, more or less. In our, with our modification by using CAPIO, the first file is available just after 1 minute. So you can check the file and maybe discover that the simulation was wrong. You have to restart. So you save quite a lot of time in this case. These are preliminary numbers, so with a small simulation, just 25 hours, using not a quite so high, how to say, resolution and so on and so forth. So we are testing more and more cases here to stress the behavior of CAPIO in this application. Good. I'm going to conclude. I hope you understand a bit what is CAPIO. So basically, we presented CAPIO. CAPIO has been developed within the my project from scratch, basically. It supports POSIX standard system codes, and so it can be used in all workflows that relies on POSIX, basically, POSIX IO. Basically, what we did with CAPIO is to shift the IO coordination towards a declarative approach. So we don't want to touch the code for introducing coordination, but we extract, let's say, we separate the coordination using a separate file specifically for doing this. There are many more things to do, as you can imagine. For sure, first, develop more application, more workflows. One point that could be really interesting, and we want to do this, is to introduce multiple backends. For example, why not using ADIOS, not at the application level, but as a backend of CAPIO? So instead of using MPI, plain MPI, why not using ADIOS in our backend, in the runtime of CAPIO? For sure, we can also enhance the expressiveness of our configuration file. So the semantics can be enriched, the synchronization semantics can be enriched. Maybe we will discover that something is missing, so we will add the feature. And last but not least, this is, let me say, somehow crucial, to integrate CAPIO with existing workflow management systems, to leverage the user of writing two different files, basically, one for the workflow management system and one for CAPIO. If we enrich the workflow language, for example, CWL, we can generate the CAPIO file automatically. And this would be an improvement because the user, in that case, will concentrate only on one single file, on one single coordination model. Good. This is the team working, sorry, too fast. I concluded, but this is the team. I want to show you the name of the people involved in this team, in CAPIO. This is the Git repository and the paper describing in more details what I basically quickly described here. So if you want more details, you can take a look at the paper sketched here. Good. That's it. Thank you.
Okay. Any questions? If you're outside, please raise your hand.
See if you can see something. Okay.
No hands? You can see it. Okay. Any question for the people here in the room?
Okay.
I have one question.
Sure.
When you are making these configurations to move files from one place to another,
yeah,
I understand that we can join that with also files generated by the ad hoc file system, no? The input files can be any of the output files, so they have to be in a Unix direct, in a Linux directory or
Yeah,
similar.
it should be in a directory, not it's an ephemeral directory. It's kind of like in Hercules, you give a sort of mount point, or let me call it mount point, is not really a mount
But
point.
the mount point could be Hercules, Gecko.
The mount point
any.
is in.
But you need Unix file system, a Linux file system, a
Yeah.
BTFS or.
Yeah, indeed, we are capturing using the syscall intercept library that is used in Gecko, for example. We intercept all the system code. So currently it's not possible to have, I think at least, I'm not 100% sure, but I don't think it's possible to have Hercules or Gecko below and then on top CAPIO with this backend that we have. But for sure, the point in CAPIO is the configuration file. For sure, we could use the configuration file and the semantics using a Linux directory, as you were saying, and that directory could be mounted to Hercules or Gecko. So in principle, it's doable, but currently not, because of the backend that we have. Once we move to have multiple backend, probably we can detach, let's say, the server part from the upper part that is related to the coordination language, and then we can have multiple backend. This is something really interesting to do, because then we can leverage existing tools that are probably more optimized than CAPIO, and so we can leverage on them.
Okay.
Okay.
Thank you.
Thank you.